Good evening, ladies and gentlemen. Let's have a review of what can be an elusive topic, rational functions. We're going to analyze two rational functions, and at the end of this, we're going to graph both of these functions. So the first one, we're going to keep it fairly straightforward. First function we're going to talk about is this rational function, which is 5 times x plus 3 over x minus 3. Keep in mind that a rational function is a quotient of two polynomials. It is a polynomial divided by a polynomial. Here we have a linear polynomial divided by a linear polynomial. The first and best advice to start with is just to define the top and the bottom. The top we know is f of x. We'll just let it be f of x for the time being. Top is 5 times x plus 2, and the bottom is g of x, x minus 3. First thing we want to do is find out where the top is 0 at. The zeros of the top and the zeros of the bottom. Fairly straightforward. That's why we start off here with a rational function that is factored. It makes everything for us much easier. So we see here that the top is 0 when x is negative 2. Why is that true? Because if I put negative 2 into f of negative 2 is 5 times negative 2 plus 2, which is 5 times 0, is 0. And the bottom is 0 at x equals 3 for the same reason. G of 3 is 0. So this, I'm going to use this information a lot. Top is 0 at x equals negative 2. The bottom is 0 at x equals 3. Good, solid information that we definitely will use down the road. So let's see what we're going to do with this. The first thing we're going to do with this information is to find the domain of the darn function. The domain of that, the domain happens when the bottom is 0. And we know the bottom is 0 at x equals 3. So the domain happens when x does not equal 3. Because you cannot divide by 0. So every other real number is in the domain. Next thing we're going to do is we're going to find we're going to find the x-intercepts. The x-intercepts happen when the top is 0 and the bottom is not. The x-intercepts happen when the function itself, which is c of x, is equal to 0. A fraction is 0 when the top is 0 and the bottom is not. That's the only time a fraction is 0. And the only time that the top is 0 and the bottom is not is at x equals negative 2. This is good, solid information. And that's going to let us say that, hey, you know what? The x-intercept is negative 2, 0. Y-intercepts are super duper easy. The y-intercepts happen when x is 0. We simply evaluate the function, a rational function at 0, and c of 0 we see. If I put 0 in, I get 10 over negative 3. That's the output for 0. That tells me that 0, negative 10 thirds is a y-intercept. Nice. Next thing I'm going to do, again, I'm going to use this information that I had up here, this valuable information about the top is 0, when the top is 0, and when the bottom is 0. Good information, important, essential information. So I'm going to come down here and I want to know explosions. And I know by my definition, explosions happen when the bottom is 0 and the top is not. The only place the bottom is 0 and the top is not is at this x equals negative 3. That tells me there is an explosion at negative 3. And we know that explosions are also known as vertical asymptotes. So, and it is enough to know for us to know right now this is a big term next year in calculus, it is enough for us to know now what an explosion is on the graph. The graph explodes. So let's see what we have thus far. What we have so far is that the domain does not equal 3, all reals such that x does not equal 3. We know the x-intercept. We know the y-intercept. We know the explosion is happening at x equals 3. And now off to this elusive topic of what? The end behavior. What we want to know is, what does the graph of the function look like on its end? That is, what does the graph look like when x goes to positive infinity? And what does the graph look like when x goes to negative infinity? And determine what the graph looks like as x goes to positive infinity and as x goes to negative infinity. We're going to use this topic of a really large real number. And notice that I have that real number labeled on the x-axis. And I can do that because it is a real number. A real number is a number that you can touch on the number line, and we're going to let Kribbillion be on the number line. In like manner, we're going to let this guy over here, negative Kribbillion, be on the number line way, way, way to the left of 0. And what we're going to do is we're going to evaluate our function at this large number. So if I put Kribbillion into that function, and we realize that a large number plus 2, and I'm talking about a really, really, really large number, a large number plus 2 is just a large number. Large number times 5 is 5 times a large number. A large number minus 3 is just a really large number, i.e. Kribbillion. And so I have 5 Kribbillion over Kribbillion. That reduces, ladies and gentlemen, boys and girls, to 5. What does this statement here mean? What it means is this, is that as x goes to positive infinity, the function values tend to 5. They go to 5. What does that mean? That means that this graph of c of x way out on the end is going to look like y equals 5. In like manner, we're going to evaluate this function at this number over here, negative Kribbillion. Let's see where the function is at negative Kribbillion. Let's evaluate the function at negative Kribbillion. Let's evaluate it. I put negative Kribbillion in, and I know that negative Kribbillion plus 2 is negative Kribbillion. I know that negative Kribbillion minus 3 is negative Kribbillion. Now I have 5 times negative Kribbillion over negative Kribbillion. These rascals here are going to cancel because it's the same real number, the opposite of the same real number. Negative something divided by negative the same something is going to be 1. 5 times 1 is 5. What does that tell me? That tells me that as x goes to negative infinity, c of x is going to go to 5. What does that mean? That means that c of x, when x goes to negative infinity, is going to look like the constant function y equals 5. Tremendous information. Let's go now to the next slide and put it all together, shall we? Let's. So I know the domain, to review. I know the x-intercept. I know the y-intercept. I know the explosion. Now, ladies and gentlemen, boys and girls, I have the end behavior, aka horizontal asymptotes. For right now, don't worry about this. Just worry about what this means. So, plotting the important aspects of this graph. I have my explosion at x equals 3. Let's label that at x equals 3. I have my one and only x-intercept. My one and only x-intercept is negative 2, 0. My one and only y-intercept, any graph will at most have one y-intercept, is 0, negative 10 thirds. Let's label that. And now, look at the end behavior. As x gets big, what does the graph? The graph tends to 5. Looks like the constant function 5. So let's just put the constant function y is equal to 5. Same thing over here as x goes to negative infinity. The graph also looks like y equals 5. Now all I'm left to do is connect the dots. Let's connect the dots coming from the left. I have to go through my one and only one x-intercept, and I have to, let's make this a little bit nicer if we could, please. What has to happen? The darn thing has to explode down. I think I may be wrong, but it has to. I think we realize that it has to explode down because it can't cross the x-axis again. It only has one x-intercept. In like a manner, what has to happen here? It has to again explode up. And so that's the graph of that rational function. Let's try another one, shall we? Let's. I think we have time for another one. Oh my goodness. C of x is this rational function x plus 2 times x minus 5 over x plus 2 times x plus 5. Again, we're going to do the same thing because it's such valuable information. You could pause the video. If I'm going too fast, just pause the video. Okay, I'm back. Let's look at the top f of x. Let's look at the bottom, g of x. And I see it's fairly straightforward that the top is 0 when x is negative 2, and when x is equal to 5, this is y. This is the powerful information that I'm going to use. The top is 0 at x equals negative 2 and at x equals 5. In like manner, where's the bottom 0? The bottom is 0 at negative 2 and at x equals negative 5, and this is the reason why. It's easy to see that. Certainly easy to see that by that graph there. Oh, fiddlesticks. It is easy to see that g of x is 0 at x equals negative 2 and at x equals negative 5. And this is the powerful information that I'm going to use about the bottom being 0. So the bottom is 0 when x is negative 2 and x is equal to negative 5. First thing I'm going to do is find the domain of this function. The domain happens when the bottom is 0. And I know exactly when the bottom is 0, at negative 2 and negative 5. And I should rephrase that. Where the bottom is 0, those are values not in the domain. And that's why I say x does not equal negative 2, x does not equal negative 5. Those are values not in the domain. Next thing I want to do is find the x-intercepts. What? The X-intercepts happen, ladies and gentlemen, boys and girls, friends and neighbors, when the top is 0 and the bottom is not 0. Two things have to happen because I want this fraction here. When is a fraction 0? When the top is 0 and the bottom is not. And I look at my powerful information up here, and I see that the only time the top is 0 and the bottom is not is at 5. So I only have one x-intercept, and right there that rascal is -5, 0. I'm going to jump right to the y-intercepts. Hey, wait a minute. Big dog. What about at -2? They both are 0. Hey, we will take care of that at the next slide. So let's do the y-intercept right now. The y-intercepts, easy peasy lemon squeezy. The y-intercepts happen when x is 0. All I need to do is evaluate the function at 0. Put 0 in wherever you see x, you get -5/5, which is -1. And that tells me, ladies and gentlemen, that the y-intercept is 0, -1. Moving forward, I think it's also easy to find the explosions. The explosions happen, again, I'm going to use this powerful information. Explosions happen when the bottom is 0. I'm going to move up here when the bottom is 0 and the top is not. The only time the bottom is 0 and the top not is at this x equals -5, ladies and gentlemen. So that's the only time I'm going to have an explosion. X equals -5. And I know that explosions are also known as vertical asymptotes. So let's take this next slide now and talk about this stuff right here. I've got this x equals -2 where the top is 0 and the bottom is 0. Man, that's a messy slide. That's all right. So now let's look at x equals -2. Top is 0 and the bottom 0. All I know at this point is that we're going to do some more investigation about this value. But in general, all I know is if the top and bottom both are 0, is I have a possible hole in the graph. A possible hole in the graph. What I'm going to do is I'm going to look at this reduced version. And this is what I want to do. I'm going to look at this reduced version here. And I see that, yes, indeed, this algebraically is true. But I have to note here that I have this new function, c subscript 1 of x. And it is worth noting, it is extremely important to note that this new reduced version of the function that I wanted to analyze, the c of x, these are not equal because they have different domains. But I will tell you that this reduced version looks like and behaves just like c of x. This, ladies and gentlemen, is great news. Because now all I need to do is I need to look at this reduced version. And what I'm going to do is I'm going to try x equals -2 into my reduced version. Let's put -2 in there and see what I get. Well, what did I get? Oh, I got negative 7/3. And since this is defined, since the new version is defined at -2, guess what? I have just discovered a hole in the graph of the original function that I wanted to analyze. So this guy has a hole at -2, negative 7/3. Yay! So let's go to the next slide and gather all of our information. The domain, the x-intercept, the y-intercept, the explosions. And now I have this really nice hole. And what am I left to do? Oh, I'm left doing the end behavior. And we know that really, we don't like to do the end behavior. But guess what? It's very important that we do the end behavior. But we don't like to. We don't like the end behavior. But what is the end behavior? What we want to do is we want to talk about where does that function go as x goes to positive infinity? Where does that function go when x goes to negative infinity? Let's do the Kerbillion method and see what happens. And notice if I put Kerbillion in, I get Kerbillion squared over Kerbillion squared, which is equal to 1. So what does that tell us? That tells me that as x goes to infinity, the graph goes to 1. The graph of c of x, that's what we want to determine. What does the graph of c of x look like? And when x goes to infinity, the graph is going to look like 1. In like manner, ladies and gentlemen, if I put negative Kerbillion in, if I evaluate the function, and I can evaluate the function at these real numbers, I can't evaluate the function at infinity. I'm not allowed to do that, but I can put a really big number in, as I have done. And I think it's easy to see that if I put -1 in, pardon me, negative Kerbillion, and I still get 1. What does that tell me? That tells me that as x goes to negative infinity, the graph looks like y equals 1. The graph tends to 1, we say. And let's finalize our analyzation of this new function, looking at the domain, looking at the x-intercept, looking at the y-intercept, looking at the explosions, looking at this nice thing, the hole, and looking at our end behavior goes to 1. And here's the graph of that rascal. Noting, ladies and gentlemen, this hole in the graph. All I can tell you at this time is thank you and good luck to you. Bye.